Well, hey, statistics, here we go with section 8.6. I believe, I'm pretty sure, this is the last section in this chapter. Let me take a look real quick. I'm looking at section 8.6 in the book. I do not see a section 8.7. We are cruising through this thing. Doesn't mean we're taking a test tomorrow. We're going to have an extra practice day tomorrow. We'll do a quiz on sections 8.5 and 8.6. Then we'll do a whole review, and then we'll get a test in for chapter 8, probably next week. Here we go. The write-up for significance tests. Let's put a big fat X bar up at the top. We're still talking about significance tests for X bar, where like the null hypothesis would be something like mu is equal to 43, and the alternate hypothesis maybe like mu is not equal to 43. We haven't spent too much time talking about not equals, so let's tighten that up a little bit here. If the problem doesn't give a direction for the alternate hypothesis, like you can't tell if they're saying it's greater than 43 or it's less than 43. It just wonders if it's different somehow. Then we'll have to write it as both less than and greater than the whole at the same time. Now, how do you do that? It would look like this. The null hypothesis would be, like I said, maybe we'll go with 100. And then the alternate would be, if they're wondering if it's just changed, if it's different somehow, they don't know if it's changed higher or lower, we'll just put not equal to. I just made up 100 as a thing to make up. So let's write one with proportions. That would go like P is equal to 24%, so I'll put 0.24. And then the alternate hypothesis would be that P is not equal to 0.24. Okay, those are what two-sided alternative hypotheses look like. I think we did this in the notes last week, but things are starting to turn into a blur for me here at the end of the semester. And here's how you adjust the p-value if that happens. Okay, you do everything you're going to do anyway, just like we did yesterday. And then at the end, you multiply the p-value by 2 to account for the other tail. So our thing is, like, we shade towards the tail. Well, if it could go in either direction, then there's this tail, and then on the other side, there's the tail on the other side. So we just take our answer and multiply by 2. Like, if the null hypothesis was actually 100, I'm going to make up some numbers. I got no example for you here. If the alternate is that mu is not equal to 100, let's just make up some numbers, okay? I'm going to say X bar, we take a sample, and we get 94. You know, maybe these are IQ points for a class. Last year, the IQ was 100. They were very average. And this year, I got some people that are pretty smart, but then I got some question marks too. So I'm just wondering if my average overall is different than 100. I'm not going to name any names. That's not going to happen. I see where you think I'm going with that. But anyway, so I take one sample and I get 94. Is that convincing evidence that the mean is not 100? Well, I go with S sub x is equal to 13.2. That's my sample standard deviation. And let's say that my sample was just 6 kids. So I'm just making up numbers here. Now, I'm going to go find my t-statistic. Well, you guys learned that yesterday. The t-statistic is x bar minus mu naught over the sample standard deviation over the square root of n. So for us, my x bar, my sample mean, is 94. The suggested mean in the null hypothesis is 100. And that goes over the sample standard deviation, 13.2, and it's over the square root of 6. Well, I put that in the calculator, make sure this is in parentheses and this is in parentheses, and divide them, I get negative 1.11. So, how do I find a p-value from that? I put a 0 in the middle of a normal curve, and then I go and I find negative 1.11, let's just put it right there, and I shade in that direction. If this test was mu is less than 100, I would just do a TCDF and write down my answer. But it's not. It's not equal to. So the p-value goes like this. 2 times TCDF of negative 100 up to negative 1.11, and the degrees of freedom is 5. It's the sample size minus 1. Right? So I go to the calculator, and just because TCDF is still kind of new for you, I'm going to point it out. I go clear everything out. I go 2 times, hit second and variables, I go past normal CDF, go past the inverse norm and the inverse T. Now we're down to TCDF. I hit enter. My lower number is negative 100. My upper number is negative 1.11. My degrees of freedom are 5. So I have 2 times this probability ends up being 0.318. That is way bigger than 0.05. Now, why did I multiply by 2? Okay, the p-value is supposed to be the probability that if 100 is true, I would get a sample as far away as 94. But it doesn't say which way. So the 94 gives me this as a t-statistic, but it could also have been that far away or further. So now the two shaded areas are the collective probability that I would be 94 or further away. So I put it in the calculator to get one tail, and I just multiply by 2 because of symmetry. I hope that makes sense. This is way bigger than 0.05, so we would fail to reject. And I should say something about the context of the problem, like IQ points or whatever this might be about. But since I wasn't given a problem, I'm not actually going to do that. What I'm going to do is go to page 2. All right, I'm going to break down this entire big write-up for you guys, which you have to be able to accomplish. I think this is a copy from when we did this for p-hats. So I think I can go through this pretty quick. There's 11 points in this problem. You have to name the population. You have to name the parameter. It's always a mean or a proportion, right? It's always a mean or a proportion. It'll be means in this section. You have to say, we will perform a one sample t-test on the following hypotheses. So you write your hypotheses. You declare your alpha. It's always 0.05 if one isn't given. We have a random condition. We have a normal condition. You have to find the t-statistic. Then you have to find the p-value. You multiply by 2 if the ha is two-sided, like we did on the last page. Then you either reject or you fail to reject the null hypothesis and explain why in context. Now, I know I went fast, but don't you know all of this? I mean, I think you still need some practice actually reading a problem and then doing this whole write-up, but you know every single one of these pieces, and we've been practicing them piece by piece. That's why I kind of like the author, because you really have gotten this piece by piece, and now you just got to put it all together in one writing. So, having said that, look at this. Let's put it all together in one writing, people. So, I'm going to get page 542, number 4 over here, and we're going to do one big, giant write-up. Here we go, number 4. Filling cola bottles of a popular cola are supposed to contain 300 milliliters of cola. There is some variation from bottle to bottle because the filling machinery is not perfectly precise. An inspector measures the contents of 6 randomly selected bottles from a single day's production. Here are the data. So small sample size, guys. There's only 6 of them. I definitely can't use the normal or the central limit theorem to say that it's normal. We're going to have to graph that data. Do these data produce convincing evidence at the level 0.10 that the mean amount of cola in all the bottles filled that day differs from the 300 milliliters it's supposed to be? Well, all right. Here's a big old blank page. The first thing in your outline is to talk about the population, the parameter, and what kind of test you're going to do. Here we go. Our population is all bottles filled that day. The sample just came from bottles for that day, so our population is just going to be all the bottles that are filled that day. The parameter, okay. The parameter of interest, the thing we're doing this whole thing on, you guys, it's got to be a mean or a proportion. Do not tell me it's the number of any bottles. I'm tired of hearing that. It's a mean or it's a proportion. That word means mean or proportion to you. Get it in your head. This is a mean problem. So the parameter of interest is the mean. Now put some context with this. Amount of cola in these bottles. The question is it 300 milliliters? That's what we're here to answer, right? And after that, we're supposed to name what we're going to do. We will perform, I'll put a couple of these together in one sentence here. A one sample, because he only took one sample, t-test at the level alpha equals 0.10, because they actually put in the paragraph that it's supposed to not be 0.05, it's supposed to be 0.10. So now we can have a bigger number and still reject the null hypothesis. On these hypotheses, look what I did right there. I shortened it up and I rhymed a little. The null hypothesis is mu is equal to 300 milliliters. That's what it's supposed to be. Versus the alternate hypothesis. Well, here's where we have a question. Do we think that we're overfilling? Do we think that we're underfilling? Should this be mu is greater than 300? Should it be mu is less than 300? Let's bring the question back in here. Do the data provide convincing evidence that the mean amount in all of the bottles filled that day differs from the target value? So it doesn't say bigger, it doesn't say less than 300, it just wonders if it's different. When that's the case, we put that the alternate hypothesis is that it's not equal to 300 milliliters. When I do that, at the end, I got to multiply the p-value by 2. All right? Okay, so the random condition. Well, I'm looking at the paragraph. It says 6 randomly selected bottles. So I'm going to say random selection covers the random condition. And I'm even going to abbreviate a little bit right there because everybody appreciates that. Now for the normal condition. Well, if n is greater than 30, I'm good to go because of the central limit theorem. N is not greater than 30. If I'm told the population is normal, I'm good to go because it doesn't matter what the size is. If the population is normal, we're good to go. I read that paragraph again. It doesn't say anything about normal. So we got to write this. N equals 6 is too small to apply the central limit theorem. Okay, so we got to go to a graph. Now there's only 6 pieces of data. I can't make a histogram with 6 pieces of data. It's just going to be like 6 bars. So I'm going to go down here. I'm going to make a dot plot. The smallest number I see in this data is like 297, and the biggest one I see is 301, somewhere around there. So look, I'm going to go 296, 297, 298, 299. I almost put 300. Almost didn't count by numbers right. That's pretty good for a math teacher. So I'm going through the data. The first one is 299.4, so I'm going to put a 299 kind of between 299 and 300. 297.7, here's 297.7. 301, there's a 301 all the way over there. I'm halfway done. 298.9, 298.9 is going to be real close to 299 there. 300.2 is just past 300. And then my last one, 297, we'll go to 297, put a dot. Look, I don't see any real shape like a normal curve, but I also don't see any outliers, and I don't see them kind of grouped together and falling off. So a dot plot, and I'm even going to put below so that if you wanted to, you could go check out the dot plot, shows no skew or outliers. So we will verify the normal condition. Takes a long time to write these. Oof. Okay, so I named my population, named my parameter, it's a mean, named what I'm going to do, a one sample t-test. I put my significance level. I named my hypotheses. I covered the random condition and the normal condition. Now it's all math. Right? But I got to get the math from somewhere. So I go to my calculator and I hit stat and edit, and I put these 6 numbers in here already. Okay? Those are my 6 data values. If you want to look at a histogram, let's go look at a histogram if you want to see it. I don't think it's going to be helpful at all. I hit zoom 9. That doesn't really tell me anything. It's just like the dots over here. So when the data is that small, I think we just got to make a dot plot. But I didn't bring the calculator out for that. I want to go find some numbers. So I go over 1 to calc, and I do number 1, one variable statistics. And my stuff is in list 1. So I hit calculate, and I get some important numbers here. The mean and the standard deviation. So look, I'm going to write down here above my dot plot. The mean is 299.03. The standard deviation, according to my calculator, is 1.50. The sample size is 6, and so that means degrees of freedom for us will be sample size minus 1, it's 5. Okay, so I need a t-statistic. My t-statistic goes x bar 299.03 minus the mean, the null hypothesis mean of 300. It will go over sample standard deviation 1.50 divided by the square root of 6. You do actually use the real n there, not the degrees of freedom. When I put that in the calculator, I got negative 1.58. Okay, that's my t-statistic. Now I got to use the calculator to find the p-value. So for the p-value, do the same thing every time, guys. Draw the curve, put a 0 in the middle. I got negative 1.58, so I'll put negative 1.58 where it goes and shade towards the tail. It helps you to do the right thing on the calculator. I need a t-CDF, negative 100 to negative 1.58, and my degrees of freedom, which are 6 minus 1 is 5. All right, so go to the calculator. I'm going to hit second and variables. I'll go past normal CDF all the way down to t-CDF number 6. Put in negative 100, negative 1.58. Degrees of freedom are 5. And I get an answer of 0.087. However, that's not my answer, though. Because look, that's not equal to, so I got to remember to multiply that by 2 or I'm going to get the problem wrong. Because that 0.087 is less than this 0.10, but when I multiply it by 2, I actually get 0.17, which is bigger than the alpha. So the author did that on purpose. Gave me numbers where if I didn't multiply it by 2, I would get it wrong. That's kind of mean, but that's how it goes. So we'll go back to our write-up and we're going to say our t-statistic is t equals negative 1.58. I'm going to write below because I put all that math below. You should definitely show this work when you do your test. And the p-value is p equals 0.17. For that reason, we fail to reject the null hypothesis that mu is equal to 300. Now, we should say something about context about filling bottles of cola, right? Well, the null hypothesis was that it's 300, and we failed to reject that, so that might actually be true. That's all we need to say. The mean amount in the bottles that day may actually be mu equals 300 milliliters. Write that and you're good. Now, I'm definitely not going to say that it is 300 because I didn't prove that it is actually equal to 300. We don't accept the null hypothesis, we reject it or we fail to reject it. So since we failed to reject it, we're just going to say it might be the case that it's true. All right? I'm going to do the same thing I did last time at this point, guys. I'm going to turn the page here. I'm going to tell you that's your homework. So go to page 541 and read the lesson app on 8.6. On 541, what does that look like? Let me just take a look real quick. It's the stuff up in the green here. Just read that, and then I want you to just follow my directions and see if you can put a write-up together. I'll write this one up too, and then when I post it, the answers will be there. That's your homework for today. One little tiny problem. Have yourselves a good day.